NASA's Viking 1 lander may have touched down on a Megatsunami deposit in 1976. This is today's presentation's topic. On July the 20th, 1976, the Viking 1 lander made history when it touched down on the Martian surface, becoming the first spacecraft to successfully operate on the Red Planet. In this image, we can see Carl Sagan in front of a Viking lander model in Death Valley, California. One of the mission's primary goals was to seek evidence of life on Mars. We know that the presence of water is a crucial requirement for the development and preservation of life on Earth. So evidence of former water-related resurfacing became a key constraint on the landing site selection. However, locating a suitable landing site was highly challenging. As seen on the right, Mariner 9 images were sufficiently detailed to recognize broad-scale features, but not to characterize the landing site in terms of detailed geology and topography. However, Mars has some of the largest fluvial landscapes in the solar system, if not the largest. These are the circumcrisi outflow channels that you can see here in Mola topography. Red is high, blue is low. This is 2,500 kilometers. You can see that the outflow channels are immense, and their origin is attributed to catastrophic flooding from the highlands, from aquifers in the highlands. The landing site was selected to be in the Maya Valles region here. The expectation was to visually and geochemically examine fluvial landforms, perhaps similar to the streamlined landscapes of channeled scabland in Washington state, shown in this slide. Instead, we found these rocky plains at the landing site. Initially, the rocky surfaces were considered ejecta materials. However, there were not enough impact craters detected in the region. Another idea that was floated around was that the plains could be broken up lavas, but unequivocal lava fragments were found to be rare. So the nature of the landing site became an enduring mystery. So 13 years after the Viking 1 landing, the concept that Mars might have hosted a northern ocean was introduced by Tim Parker and others. In their paper, they include this map. This is the North Pole here. And you can trace here this thick black line here, traces a shoreline, an ocean shoreline that could have existed about 3.4 billion years ago. And notice the location of the landing site, the broad location within this circle along the paleo shoreline. Then in 1997, Bob Craddock and others proposed that the Viking 1 lander could be on some sort of fluvio-marine deposit. For years, the characterization of these ocean margins remained a significant challenge. This was partly because the proposed paleoshoreline features did not follow the constant elevation expected to surround ponded water bodies. However, the discovery in 2016 of two latest period possible megatsunami deposits explained the irregular elevation distribution, at least for the circumcrisi and Arabia Terra regions of the northern plains. Other regions were possibly affected by major tectonic uplift. The megatsunamis appear to have been separated by a significant time gap, during which the paleoclimate became colder. Above, you can see the older megatsunami spreading from a paleo shoreline at minus 3,800 meters, and below you can see the younger megatsunami spreading from a paleo shoreline at minus 4,100 meters. In this 2016 megatsunami reconstruction, you'll see that the proposed older megatsunami deposit actually reaches the Viking 1 landing site here, and also the Pathfinder landing site here. So here we have a regional view of the Viking 1 landing site. Here's the landing site, and you'll see that it sits on the margin of the highland-facing lobate deposit, which is here. The upslope direction is towards the upper right, towards the Google Earth insignia here. And so this lobate deposit, we interpret it as a Megatsunami deposit, and you can see where it extends over the wrinkle ridge here, which is a compressional ridge structure. There is evidence of surface scouring in the inferred direction of propagation, which is consistent with a high velocity flow that propagated over the ridge, lost velocity, and then deposited its sediments in a lobate manner here. And our hypothesis is that landing site is right on the edge of that deposit. In higher resolution, that scour wrinkle ridge area that I showed in the previous slide shows very interesting dissection patterns. For example, you can see these grooves and ridges here that dissect the rim of this crater, and this one here. You see a similar pattern here. Here the erosional pattern diverges and then tends to converge in the upstream direction. And here you have this linear ridge, all consistent with a history of a powerful, fast-moving flow that went over the ridge and eroded it. To further test whether the Viking 1 lander sits on a Megatsunami deposit, we searched for an impact crater whose formation could have triggered the Megatsunami. Our search involved 1. Identifying a crater with the right stratigraphic constraints, and 2. Checking that the numerically modeled Megatsunami not only reached the Viking 1 landing site, but also produced upper ridges that matched the 2016 mapping. However, identifying such a crater is exceptionally challenging. Part of the problem is that many impact craters within the proposed Paleoceanic basin superpose an icy geologic unit, the Vastitas Borealis Formation, which is thought to be the ocean's frozen residue. All these craters are hence younger than the ocean. This view here shows one of those craters, and notice how the ejecta blanket is on top of the Vastitas Borealis Formation. However, not all hope is lost. There is yet another impact crater population within the northern plains, one that is buried. Many of these craters are part of a heavily cratered basement dating back to the Noachian period, which is 3.7 billion years old or older. But there is a possibility that these buried craters could also include a late Hesperian population, which is the age of the ocean from which the proposed megatsunamis propagated. So we identified a possible marine crater that could have been the source of the first megatsunami deposit. Here's a crater indicated by the red triangle here and here, and we named it Paul. So Paul is outstanding in several respects. First of all, notice that it's on top of the outflow channels, immense fluvial landscapes that formed by the catastrophic floods that presumably formed the Northern Ocean. And then notice that it's covered by this deposit, this dark deposit, which is interpreted to be the second, the younger megatsunami deposit. Okay, so as a consequence of these stratigraphic relationships, we know that the crater must have formed after the ocean's generation, but before its disappearance. So this dark blue surface here represents the late Hesperian Ocean with a paleo shoreline set at minus 3,800 meters of elevation. The light blue areas represent the simulated megatsunami upper ridges, and you can clearly see that it reached the Viking 1 landing site here and the Pathfinder landing site here. So let us talk a bit about the astrobiological implications. And the first thing to consider here is the nature of the ocean, the source of the ocean. So this late Hesperian ocean is currently thought to have been sourced from aquifers. And these aquifers presumably formed much earlier in the Martian history, like 3.7 billion years ago, okay, or earlier in the planet's history. So they would have been very ancient. And their formation likely happened when Mars was a lot more like Earth, very Earth-like. So then the retention of like the aquifers in liquid form without freezing due to like geothermal heat could have sustained habitable conditions inherited from that early Mars. And then those habitable conditions and maybe like life present in that early Martian hydrosphere was transferred to the ocean through the collapse of the aquifers and the release of the floods. In this context, if we think that the Viking one lander is sampling marine sediments, then we might be looking at a biochemistry and possible like biosignatures inherited from like the very early history of the planet. Here we see a close-up view of Paul crater. Notice the Novi rim indicating a phase of extensive erosion in the region. This view here shows the location of Paul, and all the red dots are knobs that form distinct, like a very distinct cluster, okay, located between the upper shoreline, this blue line here, and the lower shoreline, the white line here. Again, the blue shoreline being at minus 3,800 meters, the lower shoreline being at minus 4,100 meters. Notice that these green star symbols depict the locations of craters that resemble Paul in the sense that they have novirims. In particular, this one here in panel B is located right here in this Novi field. Okay. What is interesting about the distribution of the knobs and the craters is that they are present outside the area of outflow channel dissection, which is broadly contained between these two black lines, this one here and this one here. This is the area in Crisi Planitia that was affected by the catastrophic flooding, right? But the Novi fields extend beyond this area of dissection. Now, at one location, up here in panel C, we do see that glaciation or glacier-like features have contributed to the degradation of the regional highlands and the production of these Novi materials or these Novi surfaces. So our hypothesis is that wet-based glaciation existed during the regression, the oceanic regression from this level to this level, and that this wet-based glaciation eroded the landscape and produced these Novi fields, and that this process could have continued occurring like during episodes of ice deposition along the boundary. The presence of wet-based glaciation would suggest a relatively warm climate during the presence of the oceans. The prospect of a relatively warm climate during the ocean's regression does make a good case for sustained habitability. However, when it comes to proposing a terrain for in situ sampling and astrobiological prospection, mud volcanoes on the younger Megatsunami deposit might be excellent targets. The image on the left shows the location of Paul crater, red triangle, within the younger Megatsunami deposit's upper ridges, dark surface flanked by the dotted line. The image on the upper right is a close-up view of the crater floor, with the location of individual mud volcanoes shown by the red dots. The bottom image shows a close-up view of the crater floor, with a single mud volcano identification noted by the blue circle. So here we have the older Megatsunami deposit, red, the younger Megatsunami deposit in yellow, and the lower shoreline from which the younger Megatsunami deposit extended at minus 4,100 meters. You will see that we superposed on this image like 4 circles that are about 300 kilometers in diameter each, and counted the mud volcanoes within each of these areas. You'll see that the older Megatsunami deposit has very few mud volcanoes. Actually, we counted a total of about 11. Whereas like the younger Megatsunami deposit surface and the ocean residue, the proposed ocean residue, have thousands of mud volcanoes within the sampled areas. And this indicates that the formation of the mud volcanoes might actually be connected to like seawater retention within the sediments transported by the younger Megatsunami deposit. And that makes the sampling of these materials very interesting in terms of astrobiology, because you could be potentially looking into the composition of the ocean and its evolution through time. So here we have a very nice summary of our proposed scenario. The shoreline here is at minus 3,800 meters. Pole crater forms, generates a megatsunami that produces run-up debris flows and run-up waterfronts. Then the ocean level recedes to minus 4,100 meters. And during the recession, we have glaciation that dissects the rim of pole crater into this knobby texture. Then a second megatsunami is released from a lower ocean level, like this minus 4,100 meter level, and covers pole and part of the older megatsunami. Then glaciation continues. We have like eskers on this older megatsunami deposit, and mud volcanism forms when water entrapped within the younger Megatsunami deposit is released. And then 3.4 billion years later, the Viking 1 lander touches down on top of this older Megatsunami deposit.